session of this meeting. I think we still have a longer session coming up, which is probably going to be even more exciting. So the speaker in this session is Dr. David Weiss from Molecular Glasses. And just very quickly, not to take too much time from his talk, he is a senior scientist now at the Molecular Glass company, and his PhD is in chemistry from Columbia. He's a specialist in electrophotographic technologies, and he worked at Eastman Kodak till 2009, and now he is working at Molecular Glasses. So I'll give you a 5 minutes warning.
Okay, thank you. Thank you. Okay, good afternoon. And now for something completely different. I'm going to talk about a startup company. And we're a materials company, a chemical company. The name of the company is Molecular Glasses. To a chemist, that has some meaning. We're talking about small molecule, amorphous, glassy materials. And semiconductors, in the sense of organic semiconductors, which my physicist friends usually cringe when I say that. We're talking about organic insulating materials that are conductors when charge is injected into them. So these are organic semiconductors in that sense. And we're going to apply these to OLEDs, organic LEDs, which is a new display and lighting technology that I think everybody's probably familiar with. Talk about that a little bit. And I'll describe how our materials are, we hope, going to help revolutionize this display industry. I've had 3 careers. One academic, in academia, one in industry, and the third one in a startup. So for me, it's kind of interesting to see how a startup functions. It's a new experience for me. Kind of different. We were incorporated in 2015, and this is sort of my look, just sort of an overview of what I sort of saw as I was getting into this, not knowing exactly what I was getting into. And that is, a friend had, this sort of got screwed up. I guess you can read it. A friend had an idea, sort of a vision, to how to use some chemical technology that wasn't being used in the OLED industry that might, in a sense, revolutionize it and help it to develop. He formed a team, and initially 3 people. I'll show you pictures. And one of the things you need is funding. And I have this green stuff here, and that's really important. That green stuff is really important. But there are other things that are involved, and as I've become more immersed in this, it turns out that you need a lot of expert advice on all sorts of things. Marketing, for example. When marketing gets involved, you get a nice logo, this little thing up here. You get polo shirts. And that's important because now you have a product you have to sell. So you want to get some sort of a name recognition from this. The thing that comes out of this team is some sort of a business plan that's multifaceted. You have to have some sort of a business plan to get investors interested. And you also, for us, we need a technology focus because we have a technology, but we're a small team. And we have to focus or we're not going to get anything accomplished. Here's our team. Here's Mike Malaire, who had the idea. Mark Juba, COO. Mike is a chemist with an MBA. Mark is a chemical engineer with extensive experience in commercialization, and I'm actually research director. My experience is in research, the photophysics and photochemistry of electronically active organic materials. The 3 of us started, we were all what you call maybe Kodak graduates of the Eastman Kodak company, and Mike had this idea, collected us, recently joined by Mark Sperry as his chief marketing officer. Mark has extensive experience in startup companies. And we have Joe, who's our lab manager, who's in the audience, Dan Clark, organic chemist who's in the audience. Raj is actually out in California, along with Mike, Mark, and Mark at the SID display, Society for Information Display Exposition, selling our materials to the big companies. This last semester, we were also joined by Ray Gao, University of Rochester chemical engineering student. She was supposed to be here, but had a car accident the other day and couldn't make it. But she's going to be a graduate student in chemical engineering starting the fall here at Cornell. We've had lots of support. I want to mention the Jumpstart program here at Cornell was instrumental in getting us going. We're a materials company. It's not like a software company. You know, we need a little more than a desk and a computer. We need laboratory space. We need chemical equipment. We need analytical equipment. This takes a lot of funding, and they also mentioned a lot of expert advice. We've been funded by and given advice by all these people. So talk about OLED. Everybody knows what an OLED is, right? Organic LED. If you've got an Apple Watch, you have an OLED display. The iPhone X is an OLED display. Large displays, LG makes an OLED TV. Samsung is sort of on the borderline of making an OLED TV. Lighting, OLED Works, a Rochester company, makes OLED lighting. You don't see much OLED lighting. You know, lighting like this. Or you can buy OLED lighting at Home Depot. Very expensive. You want a little light for your living room or something, it costs you, $300 or $400. There's a reason for that. And the reason is that these things are all manufactured using vacuum deposition, essentially planar technology. It's a very wasteful and expensive process. In order to lower the cost, you need a new process. Lower manufacturing cost. The other thing is, especially for display, large display, it turns out that the color quality, particularly of a blue pixel, is too short-lived. The blue pixels tend to fade with life, and that's why some of the places like Samsung have not commercialized the OLED TVs. So you need improved performance. So what are the solutions? Lower cost fabrication. A lower cost fabrication is printing. You want to be able to print these things. If you can print them, the cost is dramatically reduced. But the materials that are used today are not suitable for printing. Our materials will help to bridge that gap. So here basically is sort of a schematic of an organic light-emitting diode. Essentially, 2 or 3 layers. LEDs were invented at Kodak around 1980 by Ching Tang and Steve Van Slyke. It's a Kodak invention that Kodak decided had no future and decided not to support. Basically, it's organic material sandwiched between 2 electrodes, a hole-injecting electrode and an electron-injecting electrode. Next to the hole-injecting electrode, there's an organic material to transport positive charge. Next to the electron-injecting electrode, there's a material to transport negative charge. Those charges meet in the middle. This could just be an interface. More typically, it's an actual layer doped with an emitting material. Those charges recombine, and they recombine on the emitting material and give off a photon. Typically, one of the electrodes is not transparent, one is, and the light comes out through the transparent electrode. So what are the organic material characteristics that are of interest? What you want to know in a molecular sense is the highest occupied molecular orbital is where positive charge will be injected. So you want to know what energy that is with respect to vacuum. The same way, electrons are injected into lowest unoccupied molecular orbital, and you want to know what that is with respect to the vacuum. You also want to know what the photon energy is here, and what the excited state energies are of the other materials, so you don't quench the photon energy that you want to have be emitted. So these are the things you want to know: homo-lunar energy, fluorescence energy, triplet energy. You also want to know the mobility of charges through these guys. mobility of charges in organic materials is notoriously slow. But these are very thin layers. These are 20, 50 nanometer layers. And so even though the mobility is slow, it's adequate for rapid switching. So what do? We make the materials that will go into those three layers: the electron transport material, the emitter layer, and the hole transport material. We make those types of materials. But in 2015, this was a $1.3 billion market. What we might address, say, in 2020 is a $4 billion market. It's a huge market, so there's a big opportunity to try to capture some of this market with our materials. Even though they're very thin layers, there's a lot of cell phones out there. So what's the issue with the way things are done now? This is the concept. Typically, right now, the materials that are in those layers are single molecules, right? The concept is that you need very pure single molecules to get the transport characteristics that you desire for these layers. And this would be a typical molecule. It's called MCBP. All these molecules have little acronyms because nobody wants to pronounce the names or even know what the names are. So it gets a little confusing. Chemists will recognize this as an aromatic amine. It means it's a whole transport material. So this is a typical whole transport material. And you vacuum deposit this and it'll form an amorphous layer. The problem is it tends to crystallize. And it may be microcrystals, maybe macrocrystals. And I'm sort of demonstrating this with little stars there. When you get a site of crystallization or even a site of aggregation, that's where the energy tends to collect. And that's a quenching mechanism. If the crystals get large enough, the device will short out. And this is a major failure mode for OLEDs. So again, tendency to aggregate. The other thing is that, as I said, printing is going to be the way people want to go. Want to print these things are like rocks, very insoluble. It won't dissolve anything. You can't make an ink out of these, for example, and do inkjet printing. And also, if you want to use these as a host for an emitter dopant, they're very poor solvents. So it's very hard to get emitters to stay in there without crystallizing. So what we've done is introduce new materials, which our marketing consultants have said we should call OLED IQ. Okay, it's marketing. I'm not part of marketing. They tell me this. These are non-crystallizable. They will never crystallize because it's a design mixture of isomeric materials. Okay, not a single molecule. It's a mixture of molecules, but it's a design mixture to make sure that all the energy levels we need are of the appropriate energies. They're forever amorphous. They can't crystallize. It's a mixture. Maybe 6, maybe more compounds. They're excellent solvents for emitter layers, emitter molecules. They're good. It's a mixture of molecules, so it's a good solvent. Actually, they vacuum deposit very nicely because they melt readily. It's a mixture and very uniform vacuum deposition. So in fact, these are very suitable for vacuum depositing. So they can be drop-in replacements for the materials that are currently being used. They're soluble in green solvents. They're very soluble. You can make inks out of these guys. And we have made inks, and you can actually print them. We can make them hole transporting, electron transporting, or ambipolar, meaning both hole and electron transporting. And we do that by changing the functionalities on these molecules. So what's our business model? We're going to focus on materials development and IP generation. In fact, our first patent was just issued. And we've got 20 patents pending and many more in the pipeline. Marketing. That's what my colleagues are out in California doing right now, marketing, trying to talk to people and hopefully sell some material. We intend to get revenue from material sales and technology licensing. Manufacturing, we are located in the Eastman Business Park. Right now we do our own manufacturing, small laboratory scale. We can do, half a gram of material, so enough for evaluation purposes. The intent is to use a local chemical manufacturer when we have to go to pilot scale and in commercial scale. So, one of the things people said to us was, well, this won't work because you need pure molecules. So we had to demonstrate the concept. This is where the Jumpstart program at Cornell came in. We collaborated with the group at Cornell and with the group at the University of Rochester and made this molecule. And you notice this molecule uses a coupling, organic chemistry coupling reaction with a bidentate reagent. So we're able to get a mixture of compounds. And this would be a whole transport part. This would be an electron transport part. So this is an ambipolar material, six compounds. If you look at the cyclic voltammetry in solution, what you see is in the oxidation, you see very clean 2 oxidations, and then their subsequent reduction, very reversible. And if you go in the negative direction, you see the reduction, very clean reduction, and again, very nicely reversible. That's one of the things you have to have, right? If a molecule is unstable when you oxidize or reduce it, it won't work. So it has to be able to survive that. And these molecules are very, very stable to being oxidized and reduced. So, we did this, and they said, well, it won't work. So we had to make a device, which for us is difficult because we have no capability of doing that. We needed the vacuum deposition, and we needed to make a device and then test it. So we made a device. The device was a simple whole transport layer, and in our material, sandwich it between 2 electrodes, put a field on it. The field, typically it's 5 to 10 volts, which comes out to about 5 times 10 to the 5th volts per centimeter. So pretty high fields you put on it. That enables the charge injection. And it lit up. As you increase the current, the luminance went up. Very low quantum efficiency, but we're just trying to demonstrate that it works. So this is a demonstration. We published this in the Journal of Organic Chemistry, 2015. And we've got lots of these materials. Here's just a few of them. And we give them names H2 whole transport, E2 electron transport, ambipolar, meaning transport either holes or electrons. And we have materials that can be used for blue emitters, green emitters, red emitters, for lighting, whatever. They're universal materials. Like I said, they're going to be forever amorphous, good solvents for emitters, excellent for vacuum deposition, soluble in green solvents, and transport charge. So one of the things we have to do is characterize these guys, because if we're going to try to give them, give samples or sell samples to companies, they're going to say, well, what is it? Again, this is difficult for a materials company because you need equipment to do that. And we slowly got equipment with the help of the funding that I mentioned. We got a fluorimeter, so now we can, and absorption spectrometry, we can do absorption, fluorescence emission, and phosphorescence emission. So we can determine the energies of these guys. We got a setup to do cyclic voltammetry, so we can determine the oxidation and reduction potentials. And from this information, we can get the highest occupied molecular orbital and the lowest unoccupied molecular orbital. It turns out that every company has a little different way of getting these numbers. So everybody sort of starts with spectra like this, for example, but some people use the intersection of the singlet, the fluorescence and absorption as a 0-0 transition for the singlet energy. Others use the extrapolated tangent to the fluorescence as a single energy. Others use 1/3 of the way up as a single energy. They're all different. The other thing you have to do is you want to measure the cyclic voltammetry with respect to an internal standard. We use ferrocene, but there's no no universal standard for what ferrocene is with respect to vacuum. So we have to modify these numbers depending on the company we're talking to. The other things, we measure hole mobility using time of flight with photo generation. The mobilities typically are 10 to minus 4 centimeters squared per volt second, which is the same as the vacuum deposited materials. Now I've only got 2 minutes, so this is a poster we have out there. One of our hypotheses was that our materials are great solvents and never crystallize, and we've done some collaborations with the Rothberg group at the University of Rochester, and we find that in our materials, a particular emitter has much longer lifetime. And then we did differential scaling calorimetry and found out, in fact, that that particular emitter, when it was put in a standard MCBP, tended to crystallize, whereas when we put it in our material, it didn't crystallize. So our material is definitely a better solvent, and in fact, our material followed the Kwai model. And the other thing is we can mix our things. So if we want electron and hole transport, we can mix and match to get whatever characteristics we want. And our materials work. They light up. And one of the things we found was that in this comparison, our material, the lifetime of the OLED was much longer than in the standard material. Sort of confirming our hypothesis that we would improve the lifetime of the OLED. So this is what we are. We're Molecular Glasses. We have a new website thanks to our consultants. We're making these materials. I've got some spec sheets out on the table out there, and be happy to talk to anybody who's interested. And these are amorphous organic materials that transport charge. They may have other applications. So one of the purposes of coming here is to explore what other opportunities there might be to apply these materials. So if you have, you think that you have something that might be useful for this, please let us know. Thank you.
Okay, questions, please.
You showed an example of ambipolar OLED. How do you how does it actually emit light? Where is the junction?
Typically the junction is the emitter layer. And what you want is you have holes coming one way and electrons coming the other way. And you want both of those to be able to get into the emitter layer. So having a host material that transports both holes and electrons is an advantage. Gets them into the middle. One of the things you don't want to have happen in an OLED is to have charge pile up on one interface. Then it tends to just annihilate. You don't get very good efficiency. So ambipolar would be for an emitter layer host.
What about the brightness?
The brightness is determined by the emitter layer, the emitter material.
How does it compare to the standard OLED?
Right now, we're comparable. The thing we've noticed, but these are not optimized in any way. And one of the issues is that every company, of course, has their own proprietary architecture materials. So we're going to put our materials into an unknown architecture. So, without any optimization, the best we can hope for is they behave about the same as the standard. And that's what we're seeing so far.
Please.
So what are the electron and the hole conductivity of your material?
I can't hear you, I'm sorry.
Electron or hole conductivity of your material?
Yeah, about 10 to minus 4 centimeters squared per volt second. 10 to minus 4. So it's about the same as the vacuum deposited materials in that, but very slow compared to, what physicists are used to. Yeah.
So for the cyclical punditry plot we have there, does the flatness of the current versus voltage matter? Do you care about it for your application?
No, because all we're trying to demonstrate there is that the material can be oxidized or reduced, and we want to know at what voltage that occurs. Because that voltage basically is telling us what is the highest occupied molecular orbital is, well, the lowest occupied, gives us the energies of those orbitals. And so that's important. You know, when you make a device, you want the holes essentially want to go uphill, electrons want to go downhill. So you want to have your device architecture such that you don't have any electrical barriers, any big barriers to charge motion. So that's just the way of getting the numbers. Eric.
One last question.
Back a couple of slides ago, you had a layer structure for a typical OLED. Some of your materials fit into that. Some of them are coming from other sources. Have you been able to identify a complete set which is actually flexigraphically printable, or is that still in the future?
Yeah, that's still in the future. We're working with companies on that. I can't really discuss it, but yeah, it's doable, but it's still in the future. Yeah.
Okay, well, let's thank the speaker.